to move this now. I want you to forget about those letters. What I want you to notice are a few things. Now, let's look at the actual groups. We've got group number 1 right here. And group number 1, okay, has how many electrons on its outermost shell? When we're talking about the outermost shell, we're talking about the shell that's the furthest away from the nucleus. Okay, it's on the outskirts of the atom. And if you look at this image, you'll see that the outer shell, actually I'll make that arrow a little clearer. Okay, the outer shell right here is outer shell here, outer shell, and this guy only has one shell. If you look at this, all elements in group 1 have 1 electron on the outer shell. That's a pattern. Okay, there's a reason that those elements only have 1 electron in their shell. It's going to cause them to behave a certain way. Let's look at the elements in group 2. Well, would you look at that? We've got an electron here and an electron here. 1 here and 1 here. 1 here and 1 here. I see another pattern. Okay, if we look at that last element, or that last electron shell, we see that everything in group 2 has 2 outermost electrons. There's a pattern. What about group 3? Okay, Roman numeral 3. They have 3. What do you think number 4 is going to have? They're going to have 4. What do you think group number 5 is going to have? What about number 6, number 7, and number 8? Okay, now these are for the Roman numerals. For the Arabic numbers, this is still 1, 2. This is 13, 14, 15, 16, 17, and 18. So I'm actually going to write this out as Roman numerals so you don't get mixed up. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So when an element is in an actual group, all elements in the same group have the same number of electrons on their outermost shell. That is known as, the number of electrons in your outermost shell is known as your valence shell. All right, valence electrons we will talk about later. Okay? Now, if I want to erase some of these drawings here, okay, so we've looked at the groups. What do we notice if we read the periodic table from the left side to the right side? How, in period number 1, how is hydrogen different from helium? Okay? The atomic number increases. As we move from the actual left side of the periodic table towards the right, the atomic number in that row goes up and up and up and up. We've got the smallest over here and the largest atomic number over here. Okay? Now, we see that on every period. This one goes from smaller to bigger. This one goes from smaller to bigger. Everybody, and bigger not necessarily in size, but bigger in atomic number. Okay? From left to right. Now, interestingly enough, though, something different happens with respect to the actual size of the elements. And in your textbook, there's a nice little section on that. I believe it is on page 22 of your text. So if you look at page 22 of your text, all right, it talks about the periodicity, okay, or the size of these actual elements as we go from from left to right. Basically, elements that are on the left side, so let's say we go lithium, then we go beryllium, we'll go to boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, these are our elements on period number 2. Okay, so P2. Now, lithium has 3 electrons, or an atomic number of 3. 4, 5, 6, 7, 8, 9, and 10. And we know that this number increases. Okay, so these are, we'll call this the atomic number. We know that it gets bigger as it goes from the left side to the right side. However, the size of the atom gets smaller, even though more particles are found in the atom. If you look at image 1.25 on page 22 of your text, you will see that the element for lithium is this big. Boron is slightly smaller, so it basically gets smaller and smaller and smaller, even though we get more and more and more particles, until we get to neon down here at the end. And even though neon has 10 particles, 10 positive and 10 negative particles on the outskirts of it, and lithium only has 3, lithium is larger in size. It is larger in size, but smaller in atomic mass. So this is another pattern. Okay? Now, for the final pattern, I want us to look at, we can look at this image or the last image I added. Now, notice how we've numbered the actual periods here. The first period has how many orbits on it? How many orbits are there? How many rings? There's 1 ring. How many rings are there on the second period? There are 2 rings. How many rings are there on the third period? There are 3 rings. How many rings are there on the fourth period? You guessed it, there are 4 rings. So if you're not quite sure how many rings you should draw when you're asked to draw a Bohr-Rutherford element, look at where it is on the periodic table. You will always have a periodic table given to you. Look at where it is. It'll give you an idea. Whatever period it's in, whatever row it's in, that's how many shells it needs to have. Whatever its atomic number is, that's how many electrons it needs to have. So I hope that you have a better understanding of these different patterns in the periodic table.